In Lecture 28, I'll focus on one of the transforming discoveries of the 20th century, the realization that nuclear reactions produce heat and radiation through the conversion of mass into energy. In this lecture, we'll see that much like atoms in chemical reactions, atomic nuclei can be split apart in fission reactions and joined together in fusion reactions. I'll begin, much as we did in the discussion of chemical reactions, by thinking about energy that drives nuclear reactions. Then I'll focus on the two great classes of nuclear reactions, fission and fusion. I'm going to close with some comments on the benefits and of the risks associated with our growing command over nuclear energy. Let's start by reviewing the nature of the atomic nucleus. In the last lecture, we saw that an isotope is defined by the number of protons and the number of neutrons. While there are only about 100 different chemical elements, there are over 2,000 different isotopes, as illustrated on the table of the isotopes. We've seen that isotopes can experience several different fates. Most of the atoms around us are stable isotopes that will be around for billions of years. But there are also radioactive isotopes, isotopes that undergo alpha decay, where a nucleus emits 2 protons and 2 neutrons, an alpha particle, and drops back 2 places in the periodic table. And we have beta decay, where a neutron spontaneously becomes a proton, an electron flies off, and the element jumps up 1 place in the periodic table. And then we have gamma radiation, where a nucleus spontaneously emits a very energetic wave of electromagnetic radiation. Isotopes can experience other fates as well. They can fuse together. They can split apart, as they constantly do in stars. On Earth, as we shall see, scientists and engineers have to help these processes along. The fact that some isotopes are stable and some are radioactive tells us that different isotopes have different nuclear potential energies. I want you to recall the chemistry analogy of the steep-walled valley. Remember driving down the valley with boulders strewn, some on the floor of the valley, some up the rim of the valley, some halfway down, perched on ledges and depressions. Well, isotopes are very much the same way. Things like uranium and radium and other radioactive elements have high nuclear potential energies. They're high up on the wall of this valley. They're ready to come tumbling down, spontaneously falling to a lower energy state. That's why radioactivity spontaneously releases energy in the form of speeding particles. That energy is quickly converted into heat. Now think about where that energy has to come from. This is a first law of thermodynamics problem, because the total amount of energy in a system is constant. So if you're producing heat, that heat has to come from someplace. And it's Einstein's theory of relativity that told us what? It's the mass of the particle itself that's being converted to heat. And so in any radioactive decay, the mass of the particles after the decay is slightly less than it was before. Now, extremely massive nuclei aren't the only ones that can release energy in nuclear reactions. It turns out that hydrogen has an incredibly high amount of nuclear potential energy in its single proton. Indeed, you can fuse hydrogen with another hydrogen atom to form helium and release a huge amount of energy in a nuclear fusion reaction. And indeed, the helium atom will weigh less than the original 2 hydrogen atoms that formed it. Now, there's an analogy to chemistry here. You can combine elements to form compounds. You can also take a compound and split it apart. And in certain cases in chemistry, in each case, you can create energy in the process. You can burn hydrogen and oxygen, fuse them together, if you will, in a chemical process to make water. But you also can take many explosive materials, and as they split apart into smaller molecules and atoms, they also release energy. So there are chemical analogies to these processes. Remember I told you that iron-56 has a special place in nuclear physics. Well, it's because iron-56 is the ultimate nuclear ash. Iron-56 with 26 protons and 30 neutrons can gain no energy either by adding neutrons or protons or subtracting neutrons and protons. There's nothing you can do to iron-56 to give you more energy, and therefore it has the lowest possible energy state. It's like the boulder at the very lowest depression in the bottom of the valley. And that's a very significant fact in terms of stellar evolution. When a star reaches iron 56 in this evolution, something very interesting happens, as we'll see in a couple of lectures. This lecture is going to focus on two kinds of nuclear reactions. First, we're going to examine nuclear fission in more detail. Some heavy isotopes, most notably uranium-235 and plutonium-239, release prodigious amounts of energy when they split apart in this process called fission. Under most situations, fission is triggered by a collision with a particle such as a neutron. Now, uranium-235 is a very important example of this process. This isotope can be split apart when a neutron comes along and hits that nucleus, and 235 just spontaneously breaks apart. The products from that original nucleus are two large chunks of roughly equal size. Plus, you produce energetic neutrons that carry energy away. Fast-moving neutrons then turn into heat as they collide with other particles. The products of the original nucleus also include two large chunks, which are essentially isotopes themselves. They're new isotopes that are very commonly radioactive. If you look at the periodic table, you can sort of track where some of these are. For example, on the left side of the periodic table, we find strontium-90, a radioactive isotope, a member of the alkaline earth group. We also have cesium, radioactive cesium isotopes, 137 and 139. Those are alkaline metals. And you remember those alkaline metals react so strongly with things like the halogens in salt. If you look at the right side of the periodic table, you'll see other radioactive isotopes produced by uranium-235 fission. These include iodine-129. Iodine's one of those halogens that reacts violently with its surroundings. And also krypton-85. Krypton is one of the inert gases. So krypton radioactive atoms go flying off into the atmosphere as isolated individual radioactive atoms. Now, the energetic neutrons that are produced by one of these reactions are available to split other uranium-235 isotopes. So if you have a high enough concentration of uranium-235, you get a chain reaction. Each fission reaction triggers new reactions in the neighboring 235 atoms, and you can have a chain reaction in this way. A nuclear reactor is nothing more than a device that controls this nuclear fission chain reaction. It's basically a big machine that converts one kind of energy into other kinds of energy. In modern commercial reactors, you use uranium fuel. Sometimes that fuel is just normal uranium out of the ground, and sometimes you enrich it in uranium-235. It's shaped into long pencil-thin rods, and those rods are then encased in zirconium metal. That metal casing prevents new radioactive isotopes from escaping into the environment. For example, the krypton, which is a gas. You don't want that escaping in the environment, so you encase the fuel rods. Fuel rods are arranged in a regular pattern so they can irradiate each other with neutrons, and a typical nuclear power plant may have several hundred, even a few thousand of these individual fuel rods that are arranged in easily installed units. So you pull out one unit of a few fuel rods when it wears out, and you just stick another one in. It's a very efficient and fast operation in nuclear power plants. There's a fluid, either normal water or sometimes it's heavy water, that is deuterium water, water with the deuterium isotope of hydrogen, and that surrounds the fuel. This water absorbs some of that energy from the neutrons, and the water gets very hot. There are also, in many nuclear reactors, graphite control rods that can absorb neutrons and be used to shut down the reaction if you want to cool things off. The central reactor core has to be surrounded by a reinforced steel structure, an extremely strong structure, to prevent any leakage of that radioactive material. That's a critical part of all nuclear power plants. So you're generating heat. You're generating heat in the reactor core, and that heat is used to produce steam. The steam is used to drive a turbine and an electric generator, and it's just like a coal-burning power plant. The only difference, in fact, between a nuclear reactor and a coal-burning power plant is how you generate the heat. There are now about 103 nuclear power plants in the United States, in all parts of the country. The original plans were to have far more than that. They originally were thinking of having hundreds upon hundreds of power plants in this country, but safety concerns greatly limited the feasibility of designing and building more. My wife and I have a home very close to one of these power plants, the Calvert Cliffs nuclear power plant. And we get reminded of the potential dangers every year when we receive a brochure on what to happen in an emergency. The brochure describes to us some of the types of accidents that are very unlikely to happen, like a small release of radioactivity. It also conveniently gives us a map to tell us our escape route in case there's anything about to happen. It's reassuring to know that we can get out of the way of harms if a radioactive event occurs. So that's a typical power plant safety instructions, and there really have been very few nuclear accidents. There were, however, some important historical accidents that you've probably heard about. In 1979, 3 Mile Island near Harrisburg, Pennsylvania, had a partial meltdown. This is a case when reactor water escaped from the core, so the core kept getting hotter and hotter, but the computer test systems failed, and people thought that, in fact, there was too much water in the core. Well, the result was that the whole inner core became unusable. Fortunately, there was very little, if any, radioactive leak, so this was not a danger to the surrounding community. The containment held, but it meant that very expensive facility became useless and is a large radioactive hazard for many, many years. A much more serious accident occurred in 1986 in Chernobyl in the Ukraine. That's a location near the Russian and Belarus borders. There was a complete meltdown. It produced incredibly high temperatures, and the confinement structure blew up. There were huge fires and released huge amounts of radioactivity into the air that were carried downwind, contaminating hundreds of square miles with intense amounts of radioactivity. Many people died as a result of radioactive poisoning. Many more are sick. It's devastated the ecosystem in that area, and that's the worst case scenario. It turns out that those nuclear reactors in the former Soviet Union were not so well designed as the ones that are now operating in the United States. Now, under unusual natural circumstances, you can have hot water deep in the earth that dissolves uranium atoms out of the rock, that concentrates them, and then they can be redeposited in a uranium-rich ore deposit. Now, billions of years ago, when uranium-235 was many times more concentrated than it is now because of the half-life of uranium-235, it turns out that a few of these deposits actually became natural fission reactors in the ground. That is, the neutrons emitted by one 235 actually triggered the decay of other uranium-235 in a sustained nuclear reaction. We now know of 17 separate natural reactor sites near Oklo and Bangombe in equatorial West Africa in the Republic of Gabon. These were discovered in 1972, quite by accident, when uranium ore was shipped from these mines. And when people analyzed the ore, they said, these have been depleted in uranium-235, which is the valuable material. Someone's been getting at these ores, maybe someone who was trying to sneak uranium-235 to make atomic weapons. Well, upon further examination, it was realized that the uranium-235 was depleted because these had been natural reactors that reacted for perhaps 100,000 years, raising the local temperature by 350 degrees centigrade. For all that time, a huge amount of energy released by this natural reactor. Now, if nuclear fuel such as uranium-235 is sufficiently concentrated, you can get a chain reaction that proceeds faster and faster in an uncontrolled explosion. That's the way atomic bombs work. They use a few pounds of concentrated uranium-235 or plutonium-239, typically in a grapefruit-sized mass, and you can split that mass into several pieces. You can separate them slightly, for example. You then surround that charge with precisely shaped conventional explosive, like a plastic explosive. When that conventional explosive is fired, it mashes together all the fissionable material, and so you get a critical mass, and suddenly it explodes in an atomic bomb explosion. That uncontrolled chain reaction releases heat, releases light, radiation, and also huge amounts of radioactive isotopes from the split uranium atoms. The first atomic bombs carried the power of thousands of tons of chemical explosives. But remember, atomic bombs are inherently limited because you can only have a critical mass of material. You can't have much more than that. And so you can't just have as large a bomb as you want. That's an atomic bomb. And the history of the atomic bomb's development, by the way, is wonderfully described in a book by Richard Rhodes called The Making of the Atomic Bomb. If you'd like to know more about that amazing history, it's a great book and I recommend it. We come now to the second kind of nuclear reaction called nuclear fusion. In nuclear fusion, two nuclei combine to form a single larger nucleus. If the mass of the resultant nucleus is less than the original two particles, then energy is released in the process. By far the most common fusion reaction in nature combines two hydrogen atoms to make a helium atom. This reaction is the primary energy-producing process in the sun and in most other stars. Indeed, the sun converts about 700 tons of hydrogen into helium every second. And roughly 0.5% of that mass disappears and becomes energy. And that's the radiant energy that comes to us and radiates the entire solar system with light from the sun. Now, under most circumstances, hydrogen atoms aren't going to combine this way. The positive charges of the one proton and one hydrogen repel the positive charge of the other proton and the other hydrogen. And so the two nuclei prevent that close approach. But what you do is you form an H2 molecule with a covalent bond, as we've seen. But fusion occurs inside stars where you have tremendous temperature and tremendous pressure. And that provides the push to bring these two atoms together. You can imagine the pressure that makes the atoms get closer and closer together, temperature causing them to vibrate violently, and once in a while the two nuclei are getting close together that they actually can fuse together. You can sort of think of this as like Velcro. If you get two objects close enough together, they stick, and you form two hydrogens become the helium atom. On Earth, scientists and engineers have been engaged in several attempts now to develop nuclear fusion reactors. These would provide a wonderful sustained source of energy because hydrogen is a very cheap fuel. It's a very clean reaction. You're only producing helium after all. The principal difficulty is creating this constrained, this confined, high-pressure, high-temperature environment on Earth. Something like the center of the sun in an Earth-like laboratory. It's a very difficult thing to do. One strategy is to use hydrogen plasma. You may recall I said a plasma is this hot gas with positive ions surrounded by a negative sea of electrons. And you can confine that and compress it in a magnetic bottle. And then you can heat it with very high electrical currents, or you can hit it with a bunch of lasers and try to sustain nuclear fusion reactions. There's been a long time commitment to trying this. For example, at Princeton University at what's called the tokamak facility. That's a large donut-shaped magnet ring in which you can confine plasma and try to heat it up. Another strategy is to form tiny pellets of a compound that's very rich in hydrogen and then simultaneously hit that pellet with hundreds of lasers, high-power lasers that heat the pellet up to incredibly high temperatures. There's now a facility called the National Ignition Facility at California's Lawrence Livermore Laboratory. They have 192 of the highest power lasers known, all those lasers focusing in on a single BB-sized pellet. Well, this is taking about $500 million of our taxpayers' dollars, and the key experiment, the first of these key experiments, should take place in about 2001. It could be really exciting because what you're doing basically with that BB-sized pellet is creating a miniature sun, a miniature fusion object. So far, none of these experiments is close to a commercial plant, and it may be decades or even centuries before we have such a commercial fusion plant. But the lure of abundant, cheap energy is so seductive that I'm sure people are going to keep trying. The hydrogen bomb was developed shortly after World War II by both the United States and the Soviet Union, and it also converts hydrogen atoms into helium plus energy. There's a great book about the hydrogen bomb, also by Richard Rhodes, called Dark Sun. It chronicles the history of this development. Let me tell you how the hydrogen bomb works. You have a core of a dense hydrogen-rich compound, such as lithium hydride. Actually, rather than using normal hydrogen, you use the radioactive isotope of hydrogen, hydrogen-3, or tritium. Tritium has a radioactive half-life of 12.5 years, which is why you have to keep replenishing the material, the fusion material in hydrogen bombs. The material with a hydrogen-rich core is then surrounded by atomic bombs. Can you imagine that? You have a mass of hydrogen-rich fuel. You surround that with atomic bombs. The atomic bombs themselves are surrounded by conventional explosives. You set off the conventional explosives. That triggers the atomic bombs. The atomic bombs then create the temperature and the pressure needed to begin the fusion reactions of the central fuel. Because the hydrogen compound is inert, you can make a hydrogen bomb as large as you want to. There is no practical limit to a hydrogen bomb size. Typical modern warheads carry the equivalent of tens of millions of tons of conventional explosives. In fact, the largest hydrogen bomb I know of is a Soviet weapon, 50 million tons of conventional explosives. That's enough to destroy completely any city with a 20-mile radius of blast area. A devastating and impossible to imagine release of nuclear energy. I should tell you about one other fusion research effort. You may have read about an exciting discovery a few years back called cold fusion. Well, two scientists from Utah claimed that they were able to initiate a hydrogen fusion reaction in a benchtop experiment. All they did, they said, was to pass electric current through two platinum-like material rods of a material called palladium. And they bathed those palladium rods in heavy water, that is, deuterium-rich water. They claim when the electric current flowed, they had an excess of heat being produced, and that heat came from the nuclear fusion of the hydrogen into helium. Well, if true, this result promised unlimited cheap energy for the world. Every home could have its own little fusion reaction in the basement, just in a nice, safe container someplace buried away in the basement. Well, they announced their results at a press conference, and eventually, after quite a bit of prodding, they released the details of their experiment on the internet. Literally, thousands of scientists around the world dropped everything in order to try to duplicate these important results. And after many, many efforts, after months, after thousands upon thousands of research hours devoted to the subject, it generally found out that it didn't work. Now, some people pointed this as a great example of how foolish scientists are and how they'll jump on any bandwagon. Some people said that the fact that these results were released to the press was a failure of science. But I see it as a different way. I see science as succeeding because cold fusion doesn't work, and the scientific community very quickly showed that it doesn't work. The independence, the verifiability, the reproducibility of science is a hallmark of it. So there weren't a lot of opinions floating around. People went out, they tried it, it didn't work. It was a great triumph, a great success for the scientific method. Well, before examining the benefits and the dangers of nuclear technologies, I want to tell you about one other application of nuclear fusion experiments. You might be surprised to learn that the periodic table is not complete. Even after 100 years after Mendeleev, we still don't know all the chemical elements, and we may never know them all. Scientists, in fact, continue to search for artificial, super heavy elements, that is, elements beyond the heaviest natural known element, uranium, which is element 92. And they do this through a process of nuclear fusion. The first heavy elements were produced simply by bombarding uranium with slow neutrons, neutrons that aren't traveling very fast. And some of these neutrons, it turns out, hit a uranium nucleus and they stick. Now, when this happens, every so often, the uranium will then undergo a beta decay. Now, remember what beta decay does. It moves you up one place in the periodic table. The heaviest known element is 92, that's uranium. If you have a neutron that converts to a proton, you go to element 93, which is an element only synthesized on Earth. That's called neptunium. And then you add another neutron, you go to 94, 95, 96, 97, 98. In this way, particularly at the University of California in the 1940s and 50s, they made all the elements up to neptunium, which is 93, to californium, to berkelium, elements 97 and 98. And these all have half-lives ranging from roughly 1,000 years up to 2 million years. So once you produce these elements, you can study them in the laboratory. You can study their chemical properties. This is a marvelous set of experiments. Now, a lot more progress has been made by groups in Germany and in Russia and in the United States by attempting to fuse together larger nuclei. And here you use a different strategy. You actually create beams of two different elements, two different isotopes. You fire them at each other and hope that they collide and stick together. Indeed, in this way, all the elements up to 112 have been artificially created. The heaviest of these is the isotope 277 of the as yet unnamed element 112. That was created by colliding lead nuclei, element 82, with zinc nuclei, and that's element 30. And when they happen to stick together, you got an atom of element 112. These atoms have only been produced in very small numbers, and they have a half-life of only a few hundred millionths of a second. In fact, to identify them, what you have to do is wait for them to decay to another product, and the characteristic gamma ray that comes out has a very specific wavelength. That wavelength tells you that you found element 112 as opposed to one of the other heavy elements. I want to end by looking at the benefits and also some of the problems of nuclear technology. I think clearly there are many problems that we've read about in the newspapers, and among the most pressing of these is the nuclear waste disposal problem. Nuclear waste comes primarily from used reactor control rods. When the uranium-235 is depleted, it has split apart into highly radioactive elements, and also as a byproduct of nuclear weapons production. The largest site in the U.S. is at the Hanford facility in central Washington state, where most of the weapons-grade uranium and plutonium was produced. And the process was this. The uranium and plutonium were concentrated by dissolving all sorts of radioactive materials into nitric acid. Then the uranium and plutonium was extracted, and what's left over is literally millions of gallons of concentrated nitric acid chock full of all sorts of radioactive isotopes. Now, the waste products of these nuclear fission reactions include many different radioactive isotopes, many different chemicals. We have strontium-90 with a half-life of 28 years, cesium-137, half-life of 30 years, krypton-85 with a half-life of 11 years, and iodine-129 with a half-life of 16 years. And actually, these aren't the big problem, because all of these are going to decay to safe levels in about 300 years. You just need to store these isotopes for 300 years or so. The problem is with things like cesium-135 with a half-life of 2 million years, technetium-99, a half-life of 210,000 years. These are going to remain dangerous for thousands upon thousands of years. The problem of confining this waste for many thousands of years is compounded by decay chains, because the mix of elements under storage keeps changing as you decay from one element to another to another. Some of those combinations of elements are fine, but some of them become explosive, some of them become very reactive or very corrosive. Now, the Department of Energy is zeroing in on a steel alloy that's supposed to last for 10,000 years and hold this radioactive waste. But how can anyone be sure? No material ever created by humans has lasted for 10,000 years, especially when it's holding nitric acid that's concentrated with a brew of other corrosive elements. It's a very difficult problem. By far the most widely accepted solution is burial of canisters made of this steel alloy in a dry, geologically inert environment. The problem here is, where do you put them? What kind of container do you use? The site that people are talking about now is Yucca Mountain in Nevada. And there's already a test burial site there, and they're talking about adding more and more canisters to this site because there doesn't seem to be any place else to put it. But there are lots of questions about Yucca Mountain in Nevada. It certainly is remote. It's far away from any population center. But we don't know how the water table of this mountain varies. That is, groundwater now is very, very far below the level of the waste disposal site. But maybe over thousands of years or tens of thousands of years, the water level rises and falls. And if so, you certainly don't want your burial site to be underwater. That would be very dangerous because it could contaminate water supplies. Also, Nevada is a very geologically active area. There are lots of earthquakes in that region. Yucca Mountain itself looks like a fairly young geological feature, and we don't know how active it is. Well, whatever the solution, it's going to cost us all as taxpayers a huge amount of money, many billions of dollars. Many commentators say hundreds of billions of dollars are going to have to be spent to solve this huge problem. But don't let me end on a bad note. Nuclear science has also brought us many, many benefits, and we have to focus on those. In addition to its importance as an energy source, you can use radioactive tracers to monitor all kinds of environmental situations. For example, the flow of streams, the flow of atmospheric gases, the flow of chemicals in your own body can be traced by radioactive tracers. In medicine, specific radioactive tracers highlight the workings of the body. Radioactive glucose, for example, reveals brain function. Radioactive iodine reveals the thyroid gland and how it's working. And radioactive phosphorus compounds can concentrate in areas of active bone growth and tell doctors whether bones are healing properly. Indeed, radioactive materials are also often used to destroy cancerous tissues and save people's lives. In summary, nuclear reactions result from the fact that some nuclei have more energy than others. There are two kinds of nuclear reaction: fission and fusion, and each of these release prodigious amounts of energy by converting some of the nuclear mass into kinetic energy of speeding nuclear radiation. Humans have attempted to harness this energy with results that yield both significant benefits and serious problems. But by far, the most important consequences of nuclear processes is the energy that the Earth receives from the sun. And that's the subject of the next lecture.